I would like to introduce this topic with a somewhat different way of looking at brain activity. If you were, by analogy, if you were to lose your keys at nighttime, you would look where? Under the street lamps. And in electrophysiology of the brain, we call these street lamps alpha, beta, gamma, delta, and so on. But what I'm going to attempt to show you is that you can actually illuminate the dark areas between the street lamps. So with that, the purpose of this talk, or the purpose of this study, was to identify differences in connectivity or functional connectivity that are characteristic of schizophrenia. And we had MEG data sets. These are sampled from a larger study that of hundreds of patients, which I have not gotten to so far. So I have 15 schizophrenics. There are unaffected siblings, 10 of them, and 14 normal control subjects in these groups. And I want to make a group comparison with a method called symbolic mutual information. Now, the data were collected with a 275-channel MEG system and in a bandwidth of DC to 300 hertz. We have task-free, some people call it resting. I don't think that you ever rest unless you're really asleep. So task-free data sets. We have end-back data sets consisting of 18 blocks, roughly 25 seconds per block, 450 seconds total. And we can make pairwise measurements. This is somewhat unlike previous measures other than the transfer entropy method. Pairwise measures using symbolic mutual information to compare the entire data set, that is without respect to tasks or triggers. And the analysis I will do will take place above the oscillatory bands, mainly 50 to 300 hertz. And if anyone's curious as to why, I will be able to answer that probably after the talks are over. So we have models of information sharing, and this is yet another new way of looking at the data that we have. And one common method is looking at, would be a method of how area A communicates with area B, is to look at phase locking between those areas. That B duplicates a copy of A after some delay of the signal, and you can signal average and probably show what appears to be connectivity, but does the brain really work by copying information from one area to another? There's a question to throw out there. The other is time locking, where we look at the envelope of activity, say beta band, envelope of oscillations, and look at their correlation across the brain, and look to see if area A and area B are correlated. That's yet another method of looking at connectivity or functional connectivity. But I would look at looking at 1 and 2, phase locking and time locking. These are relatively low information rates, information rate methods of looking at the activity and the communications in the brain. Yet another one, the term that's used is homeomorphic sharing. And let me explain that a bit. Let's say that I were to speak to you as area A in English, US English, and you replied in Mandarin, for example. That, as long as there's some consistency between the message that I pass to you and your reply, statistical significance, statistical consistency, then we know that information has been shared. So you really do not even need two areas of the brain to speak the same language in order to measure their communication. Now, high frequencies look like noise. It's not noise, it's actually chaos. And one of the standard methods of understanding or making sense out of chaos is to sample the data into what's called an embedding space. So if we have a signal waveform represented by samples, if I take every nth sample, I can map that group of samples into some position in the embedding space, in the signal space. And that's a common method for showing or making sense out of chaos. This method has been used way back in meteorological measures and predicting weather patterns. For the rank vector approach, we have a time series. We select intervals, lagged intervals for samples, and we rank them, that is to remove their amplitude dependency and just simply rank their amplitudes within this short window of time. And it turns out that, for example, for a window of 5 ranks, there are exactly 120 possible combinations, 5 factorial, and those are the rank vector states. So now, mutual information, if I take a pair of locations, x and y, I can compute the counts of states. So you have the counts of x, counts of y for each state, and we can compute their probabilities and the joint probabilities, and compute the information shared. This is shared information. This is not the same as the directional information that was shown in transfer entropy. So time amplitude signals are transformed into a symbolic time series. Their probabilities are computed, and you can infer some directionality by introducing a delay in one of the time series. Now, here's some comparisons in the band 50 to 300 hertz between schizophrenics, the top, my normal controls, and their unaffected siblings. And you see that this is actually one of several thousand possible maps because we have a pairwise comparison. This represents one of the seeds. So I'm just showing one of the seeds that shows differences among these groups. There are something like 2,800 voxels, so there are 2,800 by 2,800 matrix describing this data. So this is comparing resting data or task-free data, and we get the same pattern, curiously, within back data sets without respect to 0, 1, or 2 back conditions. However, when I take, for example, a statistical comparison between the schizophrenics and the normal controls, we see, at least at one of the seeds, here's the seed location, we see frontal anterior cingulate hyperconnectivity between those regions. And it turns out that a lot of the short-range connections in prefrontal cortex are indeed hyperconnected. However, not shown here, if we look at longer-range connections, we find that they're hypoconnected, and in particular to insulin. So, some of the results. The groups tested, which I explained there, small n, turns out that there's no statistical difference between task positive, the NBAC results, and task negative, the resting state results. And that's at a false discovery rate of Q greater than 0.9999. That's a big surprise. Also, there's no statistically significant difference among the 0, 1, and 2-back trials. So I can take the blocks that I had for those particular trials, do a comparison, and they don't have any statistically significant difference. And lastly, we see highly significant differences among groups for a variety of network connections. Now, symbolic mutual information is a non-parametric method, and it's independent of source amplitude. So for example, those who have shown power-related task dependencies might not be surprised if you throw away amplitude, not to see this dependency. Task-related changes in source power have little effect on symbolic mutual information. Shared information revealed by the SMI network is sensitive to differences among diagnostic groups, but insensitive to task, and independence may be a consequence of the short time duration. So the task-dependent portion is transient, and if we're integrating over an entire data set, we shouldn't be surprised that there's no contrast among tasks. And SMI is complementary to linear measures. I don't make claims that this is a measure that is to be used above the linear methods. It's simply complementary. It's showing a different aspect of the brain activity. And since SMI measures are largely task independent, it shows that they may be very useful for clinical diagnostics because the lack of task dependency means that patient performance does not affect the results. And lastly, I would like to acknowledge my collaborators. There's my mentor, Arnold Mandel, who he contaminated me with ideas of chaos. Sorry. There's the Lieber Institute, Daniel Weinberger, who supplied the sibling study data, University of Tübingen, Suryo Sokadar, and at the NIMH NEGCOR group, Richard Coppola, Tom Holroyd, Fred Carver, and Judy Mitchell-Francis. And this study was sponsored by the Intramural Research Program at the NIMH. Thank you. Are there any questions? I'm really happy to see that those of you have survived this long talk. Questions?
To what extent is your method robust to the sort of usual beamformer signal leakage artifacts that we might get?
That's a pretty good question, and because first of all, because I'm dealing with frequencies above 50 hertz, we lose most of the correlated source problems. As far as leakage, that's not avoidable because we always have more sources than we have sensors, and of course there is leakage. On the other hand, when you look at the results, when you do group comparisons, group statistics, you tend to find rather sharply defined regions like rostral prefrontal cortex that show very strong connections that are dependent on, say, schizophrenia. So all I can say is that the results, and using false discovery rate, results are extremely robust and they seem to be spatially specific. But I can't avoid the question of linkage.
Okay, well, so let's thank Stephen once again. Well, that concludes the symposium. Thank you all for attending. And of course, don't forget it's the Technology Showcase straight away next door.
Happy hour.
Happy hour, yes.